Let us now discuss the lever arm and the sign of the torque. We're focusing here on just F1. The line of action of F1 is this dashed line. The moment arm, or the lever arm, is by definition the shortest distance separating that line of action from the pivot. Shortest distance separating that line from the pivot. The shortest distance is what's drawn here in black, is the perpendicular. It has to be a right angle here. That length is actually my lever arm. Now, if my object here can rotate only about that pivot, if we apply that force, what is it going to do? It's going to try to spin it in the counterclockwise direction. So this particular torque, the torque due to F1, its direction is counterclockwise. By convention, we use the positive sign for counterclockwise torques. So this one is a positive torque. Let's look at F2 instead. The line of action of F2 is here. This is the pivot. So the lever arm, or the moment arm, is going to be the perpendicular. She's going to be this. This is our lever arm, what I drew in black here. That distance, that's my lever arm. Now, however, since this is my pivot, if F2 is acting by itself on our object, the effect of F2 is to rotate the object in this direction, which is the clockwise direction. So the torque due to F2 is clockwise, which is negative by convention. What about F3? F3, the line of action is the dashed line here. In this case, it goes actually through the pivot point. So the shortest distance separating that line of action from the pivot point is 0, since it goes through the pivot point. So the torque due to F3 is just 0. Now what about F4? My pivot point is still here. This is my line of action. So I need to find the shortest distance. That's my shortest distance. It is perpendicular. That's my lever arm for F4. Now, if F4 acts by itself on my object, it's going to again rotate it in the counterclockwise direction. So the torque due to F4 is counterclockwise or positive. And last, let's look at F5. In dashed blue here is the line of action of F5. That's my pivot. So this is my lever arm. It's a small lever arm. If F5 acts by itself on my object, it will spin it in this direction, since the pivot point here is on its right. So that's clockwise. The torque due to F5 is clockwise direction, or negative. And then let's look again at this particular example. So I have this rod here, and the pivot is in here. Now, if we exert a force F on that rod, the line of action is this dashed blue line. Now the lever arm is actually this distance, what we call here R perpendicular. So the torque is F times R perpendicular in magnitude. In this particular case, that torque is going to rotate my rod in the clockwise direction, so it is a negative torque. Another way to look at it is through this. What, instead of considering F, what if we consider the components of F? Ft and Fr. Fr is perpendicular, radial essentially, is parallel to the radius, and Ft is perpendicular to the radius or tangential to the circle that this point will make if our rod is going to rotate. Now, the torque due to F, since F is equivalent to Ft plus Fr, is the torque due to Fr plus the torque due to Ft, like written here. Now, the torque due to Ft, what's Ft? If this angle here is phi, it is F sine phi. It's opposite to the angle. So Ft is F times sine of phi. The line of action of Ft is here. So its lever arm is R. So its torque is Ft times R, F sine theta times R. That's what we have here. However, for Fr, its line of action passes through the pivot. So its torque is 0. Now, if we go back and look at this, if this angle is phi, this angle is phi, you notice that R perpendicular is actually equal to R sine of phi. And if we replace it here, we get the same equation than what we had in here, Fr sine theta, for the overall torque.